Hello, Luke. Welcome to lesson 33. So today we're going to be talking about products of prime factors, and we're going to look at some statements about unequal quantities, which basically just means, for the second one here, we're just going to be looking at some more word problems that are actually very similar to the ones we've already done. So first, though, let's tackle this first part, the products of prime factors. And I'm hoping that this is actually mostly a review, if not entirely a review for you. You probably dealt with prime factors in previous years, and a lot of the work that we will be doing right now should be really nothing new compared to what you've already learned. So let's first start, though. I don't want to assume that you know these things, so bear with me here if some of this may be a little bit boring if it's a review. But I want to make sure that you've got this all squared away. So let's first start by talking about factors today. So real quick. All right. So factors. What is a factor? So if we think about a number, and let's just pick any number. Let's say we pick the number 12, for example. All right. What is a factor of 12? Well, the answer is a factor is just simply any number that we can use to multiply by something else to give us the 12. All right. So we need to think about the 12 as the answer to a multiplication problem. And we need to think of all those other numbers that we would have to use in that multiplication problem to get the answer of 12. All right. So for example, I might say that one way that I could get 12 through multiplication would be a 3, I'll use my algebra multiplication symbol here, 3 times 4, right? That would give me an answer of 12. So in this case, both the 3 and the 4 would be considered factors of the 12, all right? That's what a factor is. It's a number that you use in multiplication to get a certain number that we want. All right, in this case, a 12. All right, so 3 and 4 would be factors of 12. Can we think of any other combinations that might multiply out to be a 12? Well, sure. We could think of a 2 times 6, for example. That also is a 12. We could also think of a 1 times 12. That is also a 12. And if we try to think of any more, we're not going to be able to find any other multiplication problems that deal with whole numbers that would give us a 12. So these would be the factors for a 12. So if I were to just list them, I might say the factors for a 12 are a 1, a 2, a 3, a 4, a 6, and a 12. And I think I've got all of those covered there. Yeah. So these would be the factors for a 12. Notice that 1 would be a factor for any number. 1 would be a factor for 3. 1 would be a factor for 48. 1 would be a factor for 162. 1 can be used in multiplication to get any number. So the 1 is always going to be a factor, which kind of makes it a little bit trivial. We don't really care about the 1 too much because that's pretty obvious that that's going to be a factor for any given number. All right. The other one that's always going to be there is the number itself, because that would be the other factor that the 1 would have to use to get what we're looking for. So if I'm trying to find all the factors for the number 24, well, obviously 1 is going to be a factor, and obviously 24 is going to be a factor, just like the 1 and 12 were the factor for 12. So the obvious ones are a 1 and the number itself are going to be factors, okay? The other ones are actually much more interesting, and those would be the ones that we often are more interested in finding, all right? So that is just a review on what factors are. Now let's talk about prime factors or prime numbers. All right. So if we're talking about prime numbers, you might recall that a prime number is simply a number that is only divisible by 1 and itself. So if I have the number 3, this would be a prime number because the only numbers that are that this is divisible by evenly would be a 3 and a 1, right? I can't divide this by any other whole number and end up with a whole number solution. All right. Now, opposite of this, you might think of a number like the number 6, for example. This is not only divisible by a 1 and a 6, but it's also divisible by a 2 and a 3 as well. All right. So this number we would call a prime number because it's only divisible by 1 and 3. This number over here, we actually also have a name for it. It's called the composite number. All right, so we have a prime number over here, and we have a composite number over here. Prime number is divisible only by 1 and itself, and a composite number is divisible by multiple numbers, not just 1 and itself. Okay, so if we just switch this up a little bit, and instead of saying prime numbers, let's just say what's a prime factor. All right, well, a prime factor would simply be a factor that is a prime number. All right, so going back to these factors for a 12, right? We're looking at the 12 over here. Here are all of its factors. Are there any prime factors in there? Well, sure. There's actually, well, 1 is considered prime, but it's kind of trivial. We don't care much about it. 2 would be prime. That's only divisible by 1 in itself. 3 would also be prime. 4 would not be prime. 6 would not be prime. And 12 would not be prime. So in this case, we're left with just a 2 and a 3 as the prime factors for this 12. Okay, so the point that I'm trying to make is that a prime factor is a prime number. All right. Now, there's a very interesting relationship between prime factors and any given number. It's really quite cool. So if you take any number you want, let's take the number, we'll start small. Let's take the number 8. Okay. I can actually compose this as a product of prime factors. So I can actually take a bunch of prime factors and actually multiply them together to get this 8. And you may have done this previously. So maybe I'll just show you how you may have done it before. Maybe this will ring some bells for you. So what I would do is I would start dividing this by my smallest prime number that's not a 1. All right. So if we think of prime numbers, if you just started counting, you would say, well, 1 is a prime number. 2 is a prime number. It's only divisible by 1 in itself. 3 is a prime number. 4 is not. 5 is a prime number. 6 is not. 7 is a prime number. 8 is not. 9 is not. 10 is not. 11 is a prime number. And we could keep going in finding all of these primes, right? So when we're trying to write a specific number as a product of prime factors, what we're going to do is kind of disregard the 1. We don't care about him. He's trivial. But let's start with the next lowest prime factor here, a 2, and see if the 2 can go into this 8. Is it a factor of 8? And the answer in this case is sure. 2 is a factor of 8. 2 can go into 8. So we're going to write the 2 here, and we're basically going to divide it out. 2 can go into 8 how many times? 4 times, right? Now we're going to divide this one out, right? And we're going to look again. So again, starting with our smallest prime factor available, our smallest prime number, I should say, available, it's going to be a 2. So can a 2 go into this? Is it a factor of 4? Absolutely it is. And how many times can 2 go into 4? 2 times, right? And then we end up with 2, which actually is a prime number, right? Now, sometimes people will just stop here once they've reached a prime number. Others like to actually kind of finish this out and say, well, what prime number can go into this prime number? It's a 2, and a 2 can only go into itself once, and we've basically brought it all the way down to a 1. You can go either way. You can stop when you hit a prime number, or if you want to go all the way down to a 1, you certainly can. Bottom line is what you want to recognize is that these numbers that we found on the outside, disregarding the 1, these numbers on the outside, they can be used to write this number as a product of primes. All right. So note, if I take that first 2 and multiply it by the second 2 and multiply it by the third 2, I say third and I write a 3. The third 2, and I get what? I get 8, right? So 2 times 2 times 2 is 8. 8 can be written as a product of prime factors. Okay? Now this is pretty cool because the interesting part is we chose an 8 in this particular situation, but I could have chosen any number. Pick your favorite number and replace the 8 with it, and you can write it as a product of prime numbers. That's pretty cool. All right, that's a pretty interesting observation. So, for example, let's try another one. Let's say we've got the prime. Let's see, write 80. Well, let's go 82. 82 as a product of prime numbers. Okay, so, or prime factors. Let's do this upside down division sign here and go through our prime numbers. What's our first one? It's a 2. Now, recall there's a couple of hints, clues that you can use to know whether one of these prime numbers is divisible into these other numbers. And remember, the 2 is straightforward. Anything that ends with an even number is divisible by 2. So certainly this ends with an even number, so it is going to be divisible by 2. So we can write a 2 out here. Then we have to divide that out. 82 divided by 2, that's going to be 41. All right. Now we have to see, is this a prime number? Or can we find another prime number that can go into 41? This one is actually kind of interesting because even though you'd have to go a ways, we'd have to start with the 2. 2 can't do it. 3, and actually, let's review a rule for the 3 here too. 3, if you recall, can go into any number whose digits, when added up, are divisible by 3. Maybe you remember that from previous years. So if I have the number, 69, for example, and I'm wondering, is that divisible by 3? What you can do is add up the digits. So what's 6 plus 9? In this case, it's 15, right? So 15, is that divisible by 3? And the answer is yes, it is. So if that's true, then 3 can go into this number as well. So remember that rule. 3 can go into any number that where you can add up the digits, and the sum of the digits is divisible by a 3. Okay. A 5, that's pretty straightforward. Remember, a 5 can only go into numbers that end in a 0 or a 5. So, the numbers like 35, 70, 165, 190, all of these would be divisible by 5 because they end in a 5 or a 0, right? That's the easy one for that. 7 and 11, a little bit trickier. I don't think we're going to get into that too much right now. Most of the time, especially in these problems that you'll be working with, you're going to find that once you go through the 2 and then the 3 and then the 5, generally that's probably enough for you to get to the solution. But sometimes they might throw a 7 in there. So you're going to have to, if 2, 3, and 5 don't work, try a 7 and divide it out and see if it'll work out evenly. If that doesn't work, well, try an 11. All right, so you might have to do a little bit of division work, but most of the time, 2, 3, 5, and maybe 7 are good enough to get us to our answers in this particular textbook. All right, so in this case, though, I just threw out the number 82, and lo and behold, 41 is actually a prime number. So 41 can only go into itself once. So these would actually be, that's kind of boring, but these would be the prime numbers, prime factors for the number 82. All right. So let's maybe try some more that are a little bit more interesting. Let's try just an 80. Okay. So if we do just an 80, we might again jump to the 2 right away because we're ending with a 0. And remember, 2 can go anything that's ending with a 0 or an even number. So 2 can go into 80 how many times? 40 times. 2 can go into 40 how many times? 20 times. 2 can go into 20 how many times? 10 times. 2 can go into 10 5 times, and 5 is a prime number. So we've reached our prime number here. Therefore, we have all of our prime factors needed to write 80 as a multiplication problem composed of these prime numbers. Okay, so again, 2 times 2 times 2 times 2 times 5 is 80. All right, so this would be the prime factors for an 80. Okay? All right, let's maybe try another one here. Let's go with a 147. And I'm actually pulling this one right out of the book here. So let's take a peek at that. First of all, would 2 go into this number? And the answer is no, because we have an odd number at the end here. So 2 will not work. How about the 3? And if we look at it, let's add up our digits. 1 plus 4 plus 7. Remember the clue here. 1 plus 4 plus 7. 1 plus 4 is 5, plus 7 is 12. And can 3 go into 12? Yes, it can. Therefore, 3 can go into 147. And to figure out how much, we can probably kind of work this out in our head. 3 can go into 14 4 times with a remainder of 2. Bring that 2 down with the 7, that's 27. 3 can go into 27 9 times. So we end up with 49, right? Now, can 2 go into this? Remember, we go back to our smallest prime number, 2, and the answer is no. So let's go up to a 3. Can a 3 go into this? Well, 4 plus 9 is 13, and 3 cannot go into 13, so 3 isn't going to work. Our next prime number would be a 5. 5 can't go into it, so here we do have to go up to the 7, but thankfully we know our multiplication tables, and we know that 7 can go into 49. This number isn't too big, so it makes it kind of simple. How many times can 7 go into 49? 7 times, right? And now we're down to a prime number, so we can stop. All right, and again, if we wanted to keep going down to a 1, we would just say, 7 divided by 7 is 1. Okay, so the prime numbers here would be 3, 7, and 7. So the product of prime factors would be 3 times 7 equals 147. Okay? Or if they just asked for the, the prime factors, you would just say they are 3, 7, and 7. Or comma, yeah. Commas maybe. 3, 7, 7. Okay? Very good. Let's try... Well, you know what? I think that should probably do it. And again, this should be review from previous years. So hopefully none of this is coming as a surprise for you. And actually, maybe it was a little boring. I don't know. But I want to make sure that you know how to do these. All right? So let's go on to our next topic here, which again should be somewhat of a review. We're just going to look at some more word problems. Some of them maybe just a little bit trickier than others that we've looked at, but really the same methods can be employed here to solve them. So let's just try this first one, and I think we're just going to dive right into it. Why don't you go ahead and pause the video, give this one a try, and then we'll do it together. All right, so let's try this one out. So we have 3 times a number is 12 less than 45. So let's just work from left to right. We have 3 times a number. Well, we don't know what number is, so that we're just going to represent with an n. And we're taking 3 times that number, right? So it's going to be 3n. That's pretty clear, right? Then we have our is, which we know that to be our equal sign. Right? Now we have maybe the slightly trickier part here. 12 less than 45. 12 less than 45. So if we think about that, less than means subtract, right? But what are we subtracting? And what are we subtracting it from? So we're subtracting 12, right? 12 less than. We're subtracting 12 from something, all right? We're taking away 12. And what something are we taking 12 away from? Well, it's 45, right? So we're taking a 45 and we're taking 12 less than that. So we're going to subtract the 12 from the 45, okay? And there we have what we're looking for. So our equation would be 3n equals 45 minus 12. All right, and from here, it's pretty straightforward. It's just a regular equation. So if we simplify this side, we have 45 minus 12, which is what, 33? And then we have a 3n on this side. We can divide both sides by 3 to get n by itself. and we end up with n equals 11. All right, let's just check that, make sure that it works. So if we replace our n with an 11, we have 3 times 11 equals 45 minus 12. And 45 minus 12 again is 33. 3 times 11 is in fact 33, so that does check out. That would be a solution. Okay, let's try the next one here. Maybe, again, pause the video, and we'll do this one together in a second. Okay, so now here we have twice a number is 44 less than 98. This is basically the same thing as the first problem. So we have twice a number, so it's going to be 2 times something. In this case, it's a number, so we have 2 times n. We have our is, which will be equals. All right, so we have 2n equals. Now here again, we have 44 less than 98. And just make sure that you have this clear in your head. Make sure you're understanding what this means. 44 less than. I'm not taking 44 minus 98. That's a common mistake that a lot of students make. This is not saying 44 less than minus 98. No, it's 44 less than 98. So if it's 44 less than, then what we're saying is we're taking 44 away from something. So here, the way I've written this, which is incorrect, I've written it as a positive 44, but it's not. We're taking away 44. It's 44 less than. So this 44 has to be a negative 44. We're taking it away. And so the question then is, what are we taking it away from? And we're taking it away from the 98. So this needs to be flip-flopped. It's actually 98 minus 44. All right? So make sure you don't fall into that trap. It's not 44 minus 98. We're not taking away 98 from 44. We're taking away 44 from 98. All right, so make sure that's clear in your head, because that's probably the most common mistake that people make with these problems. All right, so once again, we have 44 less than 98, so it'd be 98 minus 44, right? And here we can do a little simplifying here. 98 minus 44 would be 54. And then we have a 2n, and we can divide both sides by 2. So n is going to equal what? 27? And then we'll just double check that, make sure that that is correct. So if we replace the n with the 27 equals 98 minus 44. 98 minus 44 was the 54. And 2 times 27, well, I mean, if you don't want to do it in your head, you could write it off to the side, right? Which is going to be 54. So 54 does equal 54. We know we have a good solution. All right? Excellent. Let's try another one here. So here we have 3 times a number is 56 greater than the opposite of the number. All right. Why don't we pause the video again, try this one on your own, and we'll do it together. All right. So let's select a color here. 3 times a number. Well, that's getting pretty old now. We know what that's meaning. That means 3 times n, right, is, well, there's our equal sign, is 56 greater than the opposite of the number. So this is kind of the direct opposite of the previous problem. Instead of saying, 56 less than, here we're saying 56 greater than. So now we're not taking 56 away from something, we're adding 56 to something. All right, so what are we adding 56 to? Well, we're adding it to the opposite of the number. What's the opposite of the number? This number here, the antecedent for that, you might say, what it means, what number we're talking about. Is this, sorry about that, is this number over here. So 3 times a number, and then this is the opposite of this number. Okay, so it's basically a negative n, right? Wouldn't that make sense? The opposite of the number is going to be a negative n. And we're saying 56 greater than the opposite of the number. So again, 56 greater would indicate that we are adding 56 to something, and we're adding it in this case to the opposite of the number. So we have a negative n plus a 56, right? Now we have to do a little problem solving here, equation solving, and we can't simplify either side, but we can bring all of our n's over to one side. So we will start by just adding an n here so that then we can add the n here, bring things over. So 3n plus n is 4n equals 56. Now we can divide out the 4, and we end up with n is equal to, what, 14? And if we double check that, 3 times 14 equals negative 14 plus 56. And 3 times 14, again, if you want to do it off to the side, there's nothing wrong with that to make sure you don't make a mistake in your head. 3 times 14 is 42 equals 56 minus 14. Right? I'm just taking this positive 56 and subtracting that 14. 6 minus 4 is 2, so we end up with 42, which checks out. So we know we did it right. All right, so let's go on to this next one. This one is a little bit tricky, so why don't we do this one together so that you can see how this is going to work. All right, so if the sum of twice a number and negative 14 is multiplied by 2, the result is 12 greater than the opposite of the number. Find the number. Now, this one, I might actually start with just saying, where is our equal sign? Okay, that might be the best question to ask here. It's a complicated problem with lots of things going on. We should probably just find out where our equal sign is in this whole thing. And the reason I say that is because if you read through this, we may have some issues. Remember we said is your equal indicator, right? But the problem with this one is, look at all the is's we have. We've got an is here. We have another is over here. And we also have a comma, which I had mentioned in previous lessons, is often indicative of an equal sign as well. So we kind of have a bunch of equal sign things going on here. So the first thing might be just to decide, where is our equal in all of this? All right. Now we could do that by carefully reading the problem and trying to find out which side is being set equal to the other side. In general, a good place to look, if you're unsure which one of these is to use as your equal sign, is to look for that comma, because that comma in a way kind of supersedes the other is's, okay, the other possible equal indicators. So let's go right to that comma. And if we look at it, it does make sense if we use this as our equal location, okay? If we look at this, if the sum of twice a number and negative 14 is multiplied by 2. So here we're saying is multiplied by 2. So what we're saying is this whole thing, whatever this whole thing is, it's going to be multiplied by 2. We're not really saying it equals multiplied by 2. That doesn't really make sense. What we're actually saying is that this whole thing is being multiplied by a 2. Okay? Does that make sense? So this is, it may be a little misleading. This is not indicative of an equal sign here. All right. And you might even argue that, you know, this comma and everything immediately after it, this whole section right here, this might be considered all of our equal sign. Comma, the result is. All right. So remember, result would be indicative of whatever all of this is, all the way up to here, the comma. Whatever all of that is, that's our, you know, result. Whatever we get after doing all of this, we get a result. And that result is 12 greater than the opposite of the number. Okay? So it makes sense to realize that our equals here is actually after the comma. and where it says the result is. That all kind of together indicates equality, indicates the equal sign. All right. So kind of just breaking it down like that without actually, writing any equation yet, that helps us to kind of understand where we need to go. All right. So looking at it that way, let's start breaking this down. So if I have the sum of twice a number and negative 14, well, sum indicates addition, right? So we're adding. The sum of twice a number, well, that's one addend, twice a number, and the negative 14. So we're adding a negative 14 to twice a number, all right? Now, this is where we have to be careful. This sum is then being multiplied by a 2. So be careful. We're not saying negative 14 is multiplied by a 2, all right? We're saying if the sum of twice a number and negative 14 is multiplied by 2. So what we're really saying is being multiplied here is the sum. The sum is being multiplied by 2. Okay? So watch out. Don't make that mistake and multiply the negative 14 by the 2. We need to multiply the whole sum. All right? And if we're multiplying the whole sum, what we have to actually do, I'm going to set it in brackets in this case because I already have parentheses on the inside. So we're going to set this in brackets. This whole sum right here, whatever this is inside here, that's our sum. All right? That is what we're going to multiply by 2. All right? So hopefully you understand that. That's very different than saying, 2n plus a negative 14, which is what we had. I'm just copying this down again. And if I were to just multiply that by 2, do you see how this would be incorrect? Because now I'm taking just the negative 14 and multiplying it by 2. But that's not what we're being told here. We're being told this whole thing is being multiplied by a negative 14. So when you think about using your distributive property, you have to distribute the 2 times the negative 14. It's true, but you also need to distribute that and multiply it by the 2n as well. All right? So bear that in mind. Watch out. That's another common mistake here. All right, so 2 times a number plus a negative 14, that whole sum is being multiplied by a 2. Now, we have a comma. We indicated before that this is where our equal sign is going to be. All right, and then we're going to keep going. The result, and again, all of this red over here, that's all, or this kind of a red, I guess, color that we have over here, is going to be is 12 greater than the opposite of the number. All right, so we have something, the result, I guess I'll call it magenta. The magenta color over here is 12 greater than the opposite of a number. All right, so 12 greater would indicate that we're adding 12 to something. 12 greater than. We're adding 12 to something. What are we adding it to? Well, we're adding it to the opposite of the number. What's the opposite of the number? Well, that would be just a negative n, right? So we're taking a negative n and we're adding 12 to it. Okay? Now we need to find the number. So there we go. Gosh, now we've got this really nice equation to work through. So to begin with, I'm just going to rewrite what's inside the brackets here. This could be rewritten as 2n. Instead of a plus minus 14, we're going to call it a minus 14. All right, because remember to remove parentheses. If it's a plus sign out here, we can just drop the parentheses and not worry about anything. So we end up with a negative 14. And then I'm going to downgrade these brackets to a set of parentheses. Well, actually, I'll downgrade them to a set of parentheses and then multiply that by 2. Okay, equals, and maybe just so I don't lose this negative, I'm going to write this the opposite way and write it as 12 minus n. Just makes that negative a little more obvious, and I won't accidentally lose it later. Okay, now we can simplify, so we can multiply our 2 through the parentheses here. Distributive property, right? So 2 times a 2n is going to give us a 4n. 2 times a negative 14 is going to give us a negative 28. Equals, and on this side we still have our 12 minus n. Okay. Now we can get our n's onto one side. So we will subtract, or excuse me, we'll actually add an n here and add it here. This is going to give us a 5n minus 28 equals a 12. And then we'll just add, we'll add that 28 to both sides to get our n term by itself. So we end up with 5n equals, what is this, 40. Okay, now we can divide out the 5, and we get n is equal to 8. Right? Great, a nice number there, 8. Let's plug that in and just make sure that that actually works out. So let's check it. So we have a 2 times now an 8 instead of an n, minus a 14, right? And all of that quantity, that sum, is being multiplied by a 2, equals this negative n, which we will say is a negative 8, plus 12. So 2 times 8 is, and actually I could do the inside of the brackets here first now. 2 times 8 is 16. 16 minus 14, well, that's a 2. And then we have a 2 times this 2 here on this side. On the other side, we have a negative 8 plus 12, which is a 4. And 2 times 2 is 4. So lo and behold, n equals 8 looks right. Okay? So hopefully that makes sense. Again, this is the trickiest one that we've done so far. Watch out. It was a little bit difficult to find the equal sign there. And when you're unsure, look for commas. That's usually where it's more likely to be. All right. And then just remember that this sum was being multiplied by 2, not just the negative 14. All right. Very good. All right, last one here, and then we'll call it a class. So why don't you try this one on your own, and then we'll do it together. All right, so 5 times a number. 5 times a number is 21 less than twice the opposite of the number. There's no commas in this, and if we look around, there's only one is. So that's likely the equal sign, again, like the other problems that we were working with. So let's see if that makes sense. 5 times a number, well, that would be 5n. Is, well, that's equals 21 less than twice the opposite of the number. So 21 less than indicates that we're taking 21 away from something. What are we taking it away from? Well, we're taking it away from twice the opposite of the number. Well, how could we write twice the opposite of the number? Well, the opposite of the number would be a negative n. So twice the opposite would be a negative 2n, right? So we're taking 21 less than a negative 2n. So we have a negative 2n, and we're taking away from it 21. Okay? Does that make sense? Now it's just a matter of solving the equation. So we can add 2n to both sides. We end up with 7n equals negative 21, because this crosses out. And this is going to work out so nicely. Divide both sides by 3, or excuse me, by 7. I'm thinking one thing and writing another. So 7n divided by 7, that's going to give me an n. Negative 21 divided by 7 would give me a negative 3, right? So n equals a negative 3. And that just looks awful. We're going to clean this up a bit because it's bothering me. Divided by 7. There, that's better. Okay, so let's check that, make sure that it actually does work. We have our 5 times a negative 3 equals a negative 2 times a negative 3 minus a 21. So 5 times a negative 3 is negative 15. And over here we have a negative 2 times a negative 3. That's a positive 6 minus 21. And a positive 6 minus 21 is, in fact, a negative 15. So we know that that checks out, right? So 5 times a negative 3 is 21 less than twice the opposite of negative 3. Or I should say, yeah, twice the opposite of negative 3. All right. So hopefully that all makes sense. Again, we're not really looking at anything too new today. It's pretty much review, hopefully. We discussed our prime factors, so hopefully that was ringing some bells here and giving you a little bit of a walk down memory lane. And then these word problems are very similar, just slightly more complicated, but hopefully not too bad. So, yeah, we will stop it there. Go ahead and work on your assignment for today, and I will see you tomorrow.